Hi, so today I'm going to focus on some of the work we are doing in Europe for the Deeper project. So Deeper is one of the Exascale projects in Europe. I'm going to talk about some of the areas we are focusing within the Deeper project. So I'll just give you a quick overview of the goal of the work, and I'll tell you a bit about Exascale 10, because what we are trying in Deeper is actually targeted towards this Exascale 10 middleware. And then I'll give you a quick short background of the Deeper project. Then I'll talk about what we have learned about Exascale IO intensive applications in Deeper. So Deeper really brings a repertoire of different kinds of applications that covers almost the entire spectrum of possible IO use cases. So it's a very interesting project in that perspective. So we have looked at these applications and we have learned a lot from it. So I'm going to talk about what were the key requirements for I/O based on what we looked at from Deeper. Then one of what I'm going to focus my talk on is this, this small I/O problem. We see this recurring again and again in these Exascalable applications. Then I'm going to talk about some of the drawbacks of existing schemes that try to address the small I/O problem. There's been work done at the done in the petascale realm, and there's a lot of work done by, for example, Argonne and these people trying to do collective I/O techniques. So I'm going to talk about some of the drawbacks that we think existing collective I/O schemes may have as we go into Exascale. And then I'll just present a solution framework. I don't have all the performance results yet. We are still in the process of building the architecture at this stage, but I'll just paint a picture of the solution framework that we are trying to build for this Exascale collective I/O. We call it ExCol. And then I'm just going to talk about the current status of the work and next steps. So the goal of the work is really try to build a middleware-oriented performance I/O optimization solution. So it's going to be middleware oriented, and it can be exploited by a wide variety of applications, wide variety of backend object stores, backend file systems, and everything. So it's going to be a middleware oriented I/O performance optimization solution. And the solution should be applicable for obviously wide variety of application backend stores. And what we try to do will be fed back to the Exascale 10 work that we are doing. And the solution that we are building is part of the Deeper EU project. So this is a quick overview of Exascale 10. So I don't know if you have heard about some of the work Xyratex was involved in last year. It was called Exascale IO work group. So we were trying to build Exascale IO middleware that would help applications scale into the Exascale realm. So what happened last year and the year before that was that we had a set of requirements gathering workshops where we actually invited application experts from various domains and tried to get some idea about how Exascale applications really look like. I mean, we have read a lot of papers on Exascale, and we speculate on how things may be at Exascale, but we really need the application community to come and tell us what they think is going to be like the I/O profiles at Exascale. So we had these requirements gathering workshops, and we came up with a bunch of very interesting requirements. So the workshops there was participation from the big labs, there was participation from the academics and the industry experts. So we have a set of requirements now, and I'm going to talk about how the big picture looks like in terms of what are the requirements of this kind of a middleware. So the basic premise was that there was a big gap between applications and file systems. So there's very little information that really passes from the applications to the file systems and back up from the file systems to the applications. Someone has to bridge that gap. So there's a lot of I/O middleware solutions today, but they're all sort of built in a very piecemeal way. There is no holistic approach towards trying to build middleware that can actually address a wide variety of this kind of problems. So for example, the file system interfaces are very low. You can't have things like having hints and optimization, providing a wide variety of things like what kind of layouts do you want to have. You can have like very interesting things like deduplicated layouts and compressed layouts and things like that. And things like overlapping stripes and for small IOs. These things can be captured at the IO middleware level. So we need to try and build these things in the middleware. And then there's a lot of performance overheads due to locks and synchronizations. And obviously, these cannot scale. We can actually try and capture these kind of access patterns at the middleware layer. And for example, at the middleware, you can do very interesting things like speculative read ahead and things like that, which is not really possible today. And also at the middleware, what we were thinking of is that the existing telemetry systems in file systems and the IO subsystems, they're not really mature. So there was all log analysis and things like that. It's kind of like an afterthought. So we wanted to build a very systematic telemetry infrastructure as well as part of the middleware. I'm going to talk a bit more about it. And so the basic problem is this, is that if you look at the HPC IO stack, there's this applications at the top, then there's IO middleware, there's high-level IO formats, then there's the MPI IO middleware in between, then there's the IO forwarding layers at the bottom, and then you have the parallel file system. So many of the features are repeated along these layers. When you actually strip down all these layers, so many features are repeated again, over and over again in these middleware layers. So there is really a need to try and have a holistic picture of what really needs to be done from a middleware perspective. So if you look at, for example, metadata, there's metadata available at the high-level IO libraries. They're again repeated in the parallel file system. And there's IO aggregation that happens in the MPI IO layer. Then there's IO aggregation that happens again in the IO forwarding layers. And by the time you come to the parallel file system, this entire optimizations that were done on the top is completely lost, as we have seen. So what we did was we looked at all the requirements and painted this big picture. So this was a first draft of the architecture. So you have various interfaces which looks at IO optimizations, which looks at things like distributed containers, where you have a logical groupings of data along with their metadata, and you can have different kind of performance optimization semantics on those containers. And you can have, we needed some interesting things like FDMI, this is file data manipulation interface, where you can have various apps on top of your basic IO infrastructure. For example, things like HSM, migration, and information lifecycle management, FSCK, they can all be plug-in applications that can just be plugged into the middleware framework. So there was a need for that kind of a framework. And then there was a need for the RAS component here, which actually collects a lot of data from the middleware infrastructure here, then feeds it into this simulation engine. The simulation engine is going to replay all this telemetry data and looks at what-if scenarios of what's going to happen if your, for example, workloads change. What's going to happen if you replace, for example, SSDs with phase change memory. So you look at all these, you play all these combinations in the simulation engine, and you basically learn from the simulation engine and feed back the results back into the IO infrastructure through this machine learning interface. So it's kind of a continuous feedback loop where your IO infrastructure is totally optimized for different kinds of workloads. So this was kind of the big picture of how we thought Exascale IO middleware should look like. This was purely based on the requirements that we gathered. So having spoke about Exascale IO middleware, we are just focusing on a very small piece of this. So it's a pretty big goal, obviously. It's very audacious, and it's probably multi-year, and we need to seek fundings for these different components, and we need to try and see how we can actually put them all together. So the good thing is the European Commission has recognized the need for this middleware, and it's started to fund these initiatives. So we have been funded. Some of the IO interface pieces here have now been funded, and we are doing that work as part of the deeper project. And there's another project called Mont Blanc, which is also looking at very low power exascale architectures. Even they are looking at some of the I/O interface collection pieces. So you're going to start to see some of the software pieces of this come out very soon. So this is a quick overview of the Deeper project. So Deep is an extension of the Deep project. So it's very interesting. So the essential concept of Deep is to actually break down your infrastructure into a piece that looks at very highly parallelizable code parts, and another piece that just works on non-parallelizable codes. So you look at the application, break it down into highly parallelizable and the other side. So the highly parallelizable code runs on so-called booster nodes. So it's based on the Intel Xeon Phi platform. And the cluster nodes are just standard Intel platform. So there are semantics of in the programming aspects of how you actually break down this application into highly parallelizable and non-parallelizable portion. So that was done in the Deep project, which was really looking at compute infrastructure. But what we have done in Deeper is to actually extend it to look at resiliency and I/O. I/O and resiliency were not at all addressed in Deeper, in the Deep project. So in Deeper, we actually look at a file system infrastructure for the cluster booster architecture, and we look at resiliency schemes as well. And it's very tight co-design with applications. It's continuously getting the requirements from applications, doing optimizations, feeding it back, things like that. So this is kind of the big picture for the architecture in Deeper. So you have these booster nodes, and then you have these cluster nodes. So the booster nodes is these are all PCIe form factor. You have the NICs, you have NVRAM, then you have the Intel Xeon Phi platform here. So they're all sort of arranged in so-called bricks. And then all these booster nodes are actually connected. So this is something that we are evaluating as to what kind of interconnects we need to use, because the latency requirements and stuff are a bit different. And the cluster nodes are just standard Intel Xeon, just standard platforms. And the interesting thing is that there's also something called NAMs as part of the architecture, which is called network attached memory. It's just another tier. Even the NAM is made of NVRAM itself. So the main takeaway for I/O for Exascale is that the I/O hierarchy is very deep. So basically if you look at just the memory hierarchy, you have on-chip memory over here, very high-speed on-chip memory, then you have your regular memory, then you have your NVM, then you have your network attached memory, and then you have your regular storage components. So it's a very deep I/O hierarchy. And so who are currently involved is that we have some of the biggest supercompute centers in Europe. We have Jülich and LRZ, Barcelona Supercomputing Center, and Cineca. And for the software components, we are looking at a piece of the I/O stack, and Fraunhofer is looking at providing the file system. And there's some work done by Jülich. They're bringing in an interesting middleware piece called ScionLib, which is sort of complementary to the PLFS stuff, which actually tries to look at small files and tries to gather them into a very big file. So for the I/O component of Deeper, we have Xyratex, who's looking at I/O middleware for performance optimization. Fraunhofer is providing the file system piece, and Jülich is providing the third middleware piece. The Spartak is involved, and then Barcelona Supercomputing is providing some resiliency piece within Deeper. And Eurotech is building the system along with Intel. And for the application codes, so we have a space weather application, which is brought by KU Leuven. Then we have high temperature superconductivity application by Cineca. Then we have the radio astronomy application by Astron, which is similar to some of the requirements coming out of the square kilometer array in UK, which is going to be one of the largest producers of data ever. And then you have INRIA, which is looking at an interesting application that tries to understand the effect of electromagnetic radiation on human tissue. I forget the name of the application. Then you have LRZ is looking at earthquake source dynamics kind of an application. Then Barcelona supercomputing is bringing in a it's a geoscience application. And then you have University of Regensburg, which is a lattice QCD application. So as you see from here, it's a whole host of applications from different domains. So what do we learn from these applications in terms of I/O? So for the first 3 or 4 months of the project, we were just studying the applications very closely. How they do their I/O, how are they going to scale, what are going to be its requirements at Exascale, not just in terms of like speculating, in terms of really thinking about Exascale as an issue. I just summarize the work of the last 3 months in just one slide, is that these applications really have I/O intensive modes. Unlike previously, we thought that perhaps it's mainly compute with a bit of I/O, but there are very highly I/O intensive modes in these applications. Then there is a need to address very large shared files. Of course, they do file per process as well, but there is a need to address very large shared files. You just can't avoid it. And I/O issues have to be addressed from both the checkpoint restart perspective as well as file I/O, the simulation-based file I/O perspective. And the most important thing, at least from our perspective, is that there's optimizations needed to address small I/O. Especially as you scale out, you really start to see small I/O affecting the system pretty drastically. I'm going to talk about it in the next slide. So there is a need to start thinking about small I/O from the very beginning. So we are starting to do that as part of some of the pieces that we built for Exascale 10. So just a very quick one-page summary of the small I/O problem without going into a lot of detail is most of these applications have like 4 dimensions, 3-dimensional matrices, like different applications, different processes work on different cubes. So if you think of weak strong scaling, then what you have is within this large cube, the number of these smaller cubes increases exponentially. And when you think of weak scaling, then you just the applications want to increase the size of this big cube. So we start thinking about strong scaling as well as weak scaling. So the problem is that once you do this kind of scaling, the applications, especially for strong scaling, these applications each of these processes start to do their own I/O. And this 3-dimensional mesh is converted into a 1-dimensional logical sequence here, where you have a 1-dimensional representation of a very large shared file. And all the applications, all the processes just start to dump their I/O on just a single file. You have so many I/O contentions that we start observing. There's very reduced I/O bandwidth. So we started to see these problems, and then we started asking ourselves the question as to what's out there today. Can we leverage some kind of solution today that actually tries to group these small I/Os for shared files and tries to do some kind of aggregation? And luckily, there's a lot of interesting work that was done by the ROM I/O guys from Argonne. So there is collective I/O existing today. So you can actually have this. So we started to experiment a bit with what's possible in collective I/O today. So you have if the basic collective I/O, how it works is it works in 2 phases. There's the data shuffling phase, and then there's the I/O phase. So in the data shuffle phase, what you have is that in all these processes, you aggregate. You actually assign some of the processes as aggregators. They do I/O on behalf of the other processes. So if you have these 4 processes over here, there's a couple of aggregators which are actually assigned. So these 2 are aggregators, these are the file views of each of these processes. Then there's I/O exchanges happening. So each of these processes will have a logically contiguous I/O file view that this aggregator is going to say. So this is logically contiguous. And then they start doing the I/O. So the application, from an application perspective, the application thinks, the thought is that now I/O is optimized because you've done your collective I/O and it's all fine. You start doing your very large aggregates, doing their big I/Os. You think it's all fine. But the problem is that all this aggregation and everything is oblivious of the I/O infrastructure. So you really need to know how your I/O infrastructure is at a very deep level before you try and do these kind of optimizations. So for example, things like if you try and do two-phase I/O today, so most of these, if you have all these aggregators which are trying to actually send data to, all these processes trying to send data to a single aggregator, the slowest process typically obviously causes a bottleneck. And imagine if you try to scale it up to hundreds and thousands of processes. Most of these aggregators just end up waiting because trying to synchronize. And then all these aggregators start dumping their data onto the infrastructure, and obviously it's not aware of the file layouts and not aware of the infrastructure. So all these aggregators end up having stripe collisions. And even though you try to avoid stripe collisions, what happens is that in a single I/O server, there's I/Os coming in from different aggregators, which are all out of order, and you can't do any kind of prefetching. It's all not at all optimized anymore. So there's all these problems. I mean, all these problems in existing two-phase I/O schemes. It works fine if your number of processes are manageable. But if you start if we start looking at the kind of applications we are thinking at, we have really come to the conclusion that existing two-phase I/O is not sustainable. We need something different. So this is something very interesting. So I mean, we did. I got it from one of the papers from Argonne, I think. So if you actually look at this, so the node concurrency is actually so if you look at if you look at system memory and system memory bandwidth, the factor increase is maybe about within 100. But if you look at concurrency, it's increasing by thousands. So your memory bandwidth is going to be a bottleneck if you try to use existing collective I/O mechanisms. So your memory is extremely constrained in exascale systems. The amount of memory per core is very constrained. And if you try to do things like collective I/O, assuming that you have very large buffers, that's not going to work. And your memory bandwidth is very constrained. So you really need to rethink how you do collective I/O at exascale. So we have actually proposed this solution. So this is just a big picture. So we don't want to reinvent the wheel. The Argonne guys have done very interesting work in the area of ROM I/O. So there's some very interesting features that are available today. We are going to leverage whatever we can and build on top of it. So and we're going to call it ExCol, and it's going to be part of Exascale I/O middleware. And then if you look at the big picture framework of the solution, so basically we avoid data exchanges between aggregators and processes intelligently, and we avoid very large aggregator buffers. Then also we are very aware of the physical layouts. So one of the basic paradigms for Exascale 10 is that there is a lot of awareness of the application as well as the I/O infrastructure. So we sort of build this awareness as part of the middleware. And then there's very deep I/O hierarchies in the deeper project. So we deal with the different NVRAM layers and stuff like that. So this is just an example of how we can avoid doing very large. For example, here you have logical file views. You sort of I just give an example that this aggregation, all this data shuffling was not at all required. So you could directly have used, the processes could have directly worked with their own I/O servers. And just so we are working on we have understood the application requirements. We are in the process of doing the preliminary architecture. We'll be working on the implementation later this year, and it's going to be part of Exascale 10 I/O middleware. And we are going to have very detailed evaluations for various applications, various backend file systems, including Lustre. And just acknowledge, I would like to thank the entire Xyratex team here for working. Thank OpenSFS here and EOFS and the Exascale I/O work group on behalf of whom I presented this work, and also the deeper project And I would also like to thank the 7 framework program from where we got the funding for deeper. And some key references, and sorry if the talk was a bit long, but I'm available to take questions at a later point.
I was a little late, so let's take 2 questions. If there are 2 questions. Questions?
Sai, so you auto-tune applications to optimize their I/O.
So basically, we try to introduce this concept of guided I/O, where the application can actually give some idea of how its access patterns are going to look like. So we are trying to build these guided I/O interfaces. That is something we need to see how we can incorporate that with existing applications without a lot of effort.
What's an example of an optimization?
So for example, if you look at for example, if you have a very deep memory hierarchy, if you're trying to say something like, oh, I need this data to be in NVRAM only for this amount of time. So things like that. So that's an example of guided I/O. So you need to be, sorry?
You would evict it earlier than you
Exactly. So those kind of coherency, semantics, those can all be part of the for the guided I/O stuff. And also there's some other interesting things like, for example, if you're not, you can, as part of the containerization, you could say things like this part of the file can have a deduplicated layout, this part of the file can have a compressed layout. So these kind of things can be specified from an application perspective. So those are examples.
Thank you, Sai.
Thanks.